We started with a quiz, find the average value of x squared plus y squared on the region, interval -1, 1, cross interval -1, 1. People didn't always understand this notation. I'm pretty sure it's in your first section, but it's somewhere. Okay. But I offered to explain it. People wanted me to explain it, so I did. It's simply this square. Okay. This means all the points where x is between -1 and 1, cross product of that with all the points where y is between -1 and 1, which means all the ordered pairs with x between -1 and 1 and y between -1 and 1, and that constitutes this square. Okay. Now, you want to integrate this. You can immediately write the integral, but let's make sure we understand what the integral is telling us. First of all, we can describe this region by inequalities. X is between -1 and 1, which is just equivalent to floating this interval. And -1 between y between -1 and 1. The way I read these inequalities here is give me an x. Or let's say, since I've listed x first, we're going to partition the interval from x equals -1 to 1. Well, we could draw an x-axis here, and we partition this interval. For any partition in this interval, so let's just isolate a partition right here. There's a sample point. Okay. And also, this interval corresponds to the entire rectangle between these two values of x. Okay. So we draw these two, call them vertical lines at the endpoints of our chosen interval of our partition, right? Then that interval can be partitioned with respect to y. So we partition x, that gives us a strip of y values, right? Or geometrically a strip of the region that we're integrating over. Then we partition that strip with respect to y. We don't just do one partition of y and apply it to everything, although we could do that in this case. You'll see later why we don't do that. Okay. We partition every strip that corresponds to our x partition. We partition it separately. And the reason is because you don't always have a square. So the y values for one partition might have a different range than the y values for another. Okay. So that's what's coming up. If you didn't understand that, that's okay. Just understand what we're doing here. Okay, so what we've got then, we can choose one of the little rectangles that we get. Okay. And focus our attention on that. So our x partition leave myself enough room to write that, but it says x naught is equal to -1. And we divide this up into n intervals. So we number the x values, x naught, x1, x2, x3, all the way up to xn. Maybe n is 78 billion. Or maybe it's 12. Maybe it's 4. Okay? That x sub n is going to be equal to the right limit on our x values. Y partition, in this case, is exactly the same as the x partition, except of course we've got y values, y naught less than y1. Now, instead of n, I'm going to use m on y because we don't have don't have to have the same number of subdivisions on y as we do on x. We could, on a rectangular region, we could. On a region that's not rectangular, in general, we wouldn't. Now, does all that make sense? Now, a typical interval area increment is has dimensions delta xi by delta y sub I. Okay. In other words, it's delta x sub I, delta y sub j. I is the number of this partition. Here's partition 1, 2, 3, 4. That would be partition 5, the way or increment 5, the way I've drawn it. And this would be increment 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe. Okay, I got a little vague there in the middle. Maybe it's the 9th y increment. So in that case, I would be 5 and j would be 9. If you could do a lot of them, I could be 7,587,283 and j could be 14. Okay? Give you context, make sense? This is how you understand integration, starting with partitions. It's the way you set up an interval. It's the way you figure out what in the world you're going to integrate. It's very simple in the case of a rectangular region. Now we're going to get into volume regions next week sometime, okay? Get into volume intervals. But if you had volume, well, you'd have z out here, and then for each one of these partitions, you'd have a stack of z increments. No different. If you go to 4 dimensions, well, you can't visualize it, but you can at least write them down. Okay? We won't do any 4-dimensional integrals, but you know from linear algebra, if everybody's had that you do things in 2 or 3 dimensions. And as soon as you understand what's going on in 2 or 3 dimensions, you get the dimensions you can't visualize, that you can make as many dimensions as you want to. And it's no harder, it's just longer to write it out. Okay? Similarly with integration. So we're trying to build that up. All right. So your typical increment is this. Point xi star, yj star. Now, please take my advice and make sure you understand all this completely. It's very simple, very accessible, but we're going to be using it again and again in more and more confusing, potentially confusing contexts. If you understand it very well here, then you're not going to have much trouble with it as we move on. Okay? If you don't understand it here, then you're going to continue to stumble over it. Okay, well, then the payoff here is contribution of this to the integral. Now, why are we talking about an integral? We're talking about an integral because I asked for the average value of a function, and you need to know what average value means. Divide the integral by the region. If the region is an interval of the x-axis, so it's a function of one variable, it's the length of the interval. In 2 dimensions, it's the area of the region. If you're in 3 dimensions, it's the volume of the region. If you're in 4 dimensions, it's the hypervolume of the region. Okay? The integral is the integral, but what it's telling you, well, you're developing that idea. Okay? So we're talking about an integral because I asked for an average value of a variable function. The approximate integral it's a sum from I equals 1 to n, sum over all your x partitions of the sum over all your y partitions. Okay? Now I use m sub I here for the y's. I just used m here. And now I'm going to change this to an m sub I because the number of y increments for a given increment of the x partition might change from one increment of the x partition to the next. The number of subdivisions you make on this vertical strip could depend on where you are between here and here. For given I, you're confining yourself to one little vertical strip, and we're going to let m sub I be the number of partitions, the number of increments in the y partition, okay, for that strip. Every strip can have a different number of partitions. Examples you've seen probably have the same number of X and Y partitions. You can just divide the thing into a grid. That works for a rectangle. Doesn't work so well for other shapes. Okay. So I'm being a little more general here, assuming you understand what you've seen with rectangle. Okay, so we're building this on your understanding of what happens in a rectangle, and also hopefully building your understanding, refining your understanding of what happens on rectangles. That was a bad looking eye. I'm going to make it better. Okay. Now, the sum of what? Well, the sum of the contributions. There's your sum. I think that's the same notation you see in your book. I actually read through kind of the rest of the course just to see if there's, sometimes you find something clever. I almost never open, but I haven't read it in 10 years, so I thought I'd read it last night. Okay. And so far, everything looks like what I thought it did. So I think I've been doing it consistently. I've taught this course 60 times, probably more than that. And I look, every once in a while, I look at the book to make sure my notation's correct or consistent. I didn't look at the notation that closely, but I think I saw the notation there. It's not really what I was paying attention to. I was saying, is there anything clever that they're doing in the way they develop that I hadn't thought of? Or that I maybe thought of 30 years ago and hadn't thought of since? Okay, well, all that aside, if the notation's a little different from the book, it's not difficult to reconcile it. They use asterisks for the sample points. They did one bonehead thing with a sample point in one of their pictures. I picked up on that real quick, just looked at the picture and said, what's a sample point doing there? They had a region, they had like 4 regions here. And they had a sample point right here where 4 regions intersected. Sample points have to be inside the region. They have to be interior to the region. They don't go on the boundary. Okay. I guess maybe they use this sample point for every region, which means they don't even have 4 regions. They're just using one big region. Okay. Well, that's not it. It's just the OpenStax text can use a little bit of editing, not much. Every once in a while, there's some bonehead thing that comes up. And I think that was one of them. Okay. I'm not being critical. I've never seen a text that didn't have some errors in it. Even the ones that, the university physics books that I used for years until it became too expensive. I learned out of the second edition. The last edition I taught out of was the 16th. Okay. Still love the text. I'd love to be able to use it, but it's not affordable. Okay. Approximate interval is this. Do we understand that? And it all comes, all we have to do is think about what happens in one of these 14 quadrillion increments. Okay? If you know what goes on in one increment, you can write it in general form, and you can write this sum. And then, if using notation a little bit, the limit as the maximum value of a delta x and maximum value of a delta y all approach 0, you get the integral. Provided you can define the integral with the function on the region, that's something you got to kind of pay attention to. So you get the double integral of f of x, y dy dx. And I should have put the delta yj first. Because the first summation is from j equal 1 to mi. That's the first thing that you're going to do. And the delta xi second. Just a little bonehead error of my own. Okay. But the integral has to be dy dx just because of the way we set it up. Okay. And then this would be from a to b and c to d, where this would be x equals a, x equals b, y equals d here, y equals c here. So that's general for any rectangle. What I just did doesn't apply just to this 2 by 2 square. It applies to any rectangle whatsoever. And if you've got a rectangle, then you can use the same number of y divisions as you have x divisions or whatever. Okay? It follows to solve this, which I saw in most of your papers. I've written it down a little bit sloppily, didn't have a lot of room. It's from -1 to 1 with respect to x, then -1 to 1 with respect to y inside of that. And your function is x squared plus y squared, and it's really easy to integrate. Okay. And that equals I don't really have room to work that out, I don't think, but let's start. And looking it up too much. Let's come up here. Okay. So first integral with respect to y, antiderivative of x squared is just x squared y. Antiderivative of y squared is y cubed over 3. And that would be evaluated between the limits -1 and 1. That gives you the integral from -1 to 1 of what? Well, x squared times 1 is x squared minus x squared times -1, which is plus another x squared. So we're going to have 2x squared plus y cubed at 1, you get 1/3. And at -1, you get minus 1/3. If you do 1/3 minus -1/3, you get 2/3. And that's with respect to x. Then you integrate with respect to x. The integral 2x squared with respect to x is just 2/3 x cubed. So you get 2/3 x cubed plus 2/3 x evaluated between -1 and 1. Okay. At 1, that's 4/3. At -1, it's -4/3, so you get 8/3. In check, man, I'm doing a lot of that in my head. So that agree with what some of you got? Anybody get 8/3? What's the matter with you? Did it give you time, or you missed something in the integral, or I did something bullheaded? Which one is it? See anything wrong with what I did? Better say no. No, please let me know. If you see anything wrong with what I did. Okay, one courageous soul raises his hand. Okay, I was going to then divide by the area and see if it made sense. That's our check. But I realized that when it was pointed out that I labeled this average value. And yeah, down here we started doing average value. So I started average value, but then I concentrated on the integral. I should have labeled that integral. Okay. So the average value the average value is 2/3. Divide 8/3 by 4, you get 2/3. Does that make sense? Well, what are the values of x squared plus y squared? The maximum value of x squared plus y squared occurs at these four corners, okay? And it's 2. If I go halfway to the four corners from this origin, I have x and y both equal to 1/2. You have 1/2 and 1/4, and 1/4 is 1/2, right? So the value up here would be 2, the value here would be 1/2, the value here would be 0. And that's symmetric over all quadrants of this square. Okay. If you average 0, 1/2, and 2, you get 1 1/4, which is quite a bit bigger than 2/3. So if you think it ought to be the average of those three values, then you have a little bit of a problem. If instead you think in terms of concentric circles, then this is just the radius of the circle, isn't it? Square of the radius. Okay. So the square of the radius goes from 0 up to square root of 2/2. I'm sorry, it goes from 0 to 1 within the circle. Then you got these little regions outside the circle. Okay. Now, on this circle, the value is just 1. Okay. Then the values of the corners are 2. So you have little regions where the value is greater than 1, but almost everywhere else the value is less than 1. Well, you think that through a little bit, and you think, okay, maybe 2/3 is pretty close. Okay. Another thing here. Z equals x squared plus y squared is what? It's just a paraboloid. The circular cross sections. So it's like you've got this paraboloid starting here at the origin with just one point and coming out like this and being cut by this square. You visualize that paraboloid, or even use technology to make a pretty accurate graph if you want to check to see if that 2/3 makes sense. You could do it by looking at that paraboloid and thinking about certain other things. So what we're really getting to is the soul of an integral. This is what an integral is really about. You could do a Monte Carlo simulation. You program the computer to randomly generate points within this square and evaluate x squared plus y squared at every point. Add them all up and divide by how many there are, it's 2/3. That's a handy thing to do if you don't have a means of doing a closed integral. Okay, there are better numerical methods, but Monte Carlo methods are quick and easy. Okay. Another idea you might want to store away. Okay, well, let's now apply this whole idea of partitioning and everything to I'm going to do things in terms of average values because it's something nobody ever remembers. Okay. Let's do this in the region 0 less than or x less than or equal to 2 and x over 2 less than y less than 2 less than or equal to 2 plus x. Now that region is, let's go ahead and draw a y-axis and an x-axis. Line y equals x over 2 would be like here. And the line y equals 2 plus x might be here. It really should be steeper than that, but I didn't leave myself room to make it steeper. And here's the y-axis, and here's the line x equals 2. So here's your region, bounded by this blue thing. Okay? How am I going to partition this region? Well, I'm going to say partition the x interval. Typical strip of y values will be from here to here. Make sense? Now we've got a sample point here. Okay, I'm going to draw a bigger enlargement of this partition. So here's your ith x increment, and here's your ith y strip. I'm going to exaggerate width of the increment, okay? So I can label things. There isn't room in here to label. So here's xi minus 1, here's xi. And just tell me when to stop. Somebody clap their hands. I'll keep doing this the rest of my life unless somebody claps their hands. There we go. So it's right here. So right there is what happens to be my sample point, my sample x. That's going to be x equals x sub I star. Well, then this is going to be the strip I partition with respect to y. Okay? It starts down here at f of I don't want to go there. Okay. So we start from here to here. This line here is x equals xi star over 2. Because, of course, this line is the line y equals x over 2. This line up here is the line y equals 2 plus x. And this horizontal line here is, I said x equals x sub I over 2. It's y equals x sub I star over 2. And this is y equals 2 plus x sub I star. Now, do we understand all that information? Okay. We randomly picked a sample point. We see where the sample point x equals x sub I star crosses the lower boundary, y equals x over 2. And we draw a horizontal line there, or imaginary line, y equals x sub I star over 2. And then similarly, with the y equals 2 plus x line, you get y equals 2 plus xi star. So we partition I don't remember how my colors were, but partition the y interval from xi star over 2 to xi star. So here are a bunch of y, okay, the y increments. Then we take a typical increment. Typical increment I'll take is one that's down here, which is a little easier to label. Its dimensions are delta x sub I delta x of I being x of I minus x of I minus 1, right? I think I labeled that on the last picture. And similarly for delta y, it's delta xi by delta yj. And contribution to the integral is f of xi star yj star, which is a sample point on the line x equals xi, and somewhere between the lower and upper boundary of that increment. Didn't leave myself enough room, but it's f of xi star yj star delta xi delta yj. So pretty sloppily, I equals 1 to n, j equals 1 to m sub I. Probably can't read that, but it's just like it was before. Don't have room to write it down here. Suppose we I. And it would be x sub I, y sub j, plus y sub j squared, delta xi delta yj, which then approaches the double integral. It should be delta yj times delta xi. Approaches the integral. X goes from 0 to 2. That's the interval that we partitioned, right? Y goes x over 2 to 2 plus x. Okay? Goes from this line to this line. So there's our interval in detail. Your book glosses that over a little bit, but then develops it later on. So I'm developing it now so we can kind of quickly do the rest of what you need to see for the first 3 sections. Okay? And then when you integrate this, it's easy enough. You're going to integrate with respect to y. And then when you substitute for the y's, you're going to get x's, right? And let's go ahead and do it. Integral xy plus y squared dy dx going from x over 2 to 2 plus x and from -1 to 1 equals the integral from -1 to 1 of antiderivative is going to be x y squared over 2 plus y cubed over 3 evaluated between x over 2 and 2 plus x. And that's going to be with respect to x. That's going to equal the integral from -1 to 1. And I'm just going to write it out. I'm not going to simplify it and complete the integral because you can easily do that. Replacing y by 2 plus x, and then by x over 2. And, what we get at 2 plus x minus what we get at x over 2. We get x times many ways I could have written that out. Oh, yeah, well, I wrote out the first term. Okay, that's what the xy squared over 2 gives us. And the y cubed over 3, well, we're going to substitute 2 plus x. We're going to substitute x over 2. We're going to get plus all of this integrated with respect to x. So you're going to get a bit of a polynomial there. You have to do a little bit of work. But you understand, and the thing I want you to see here is that by setting it up like this, with the x integral outside the y integral, why outside? Because we started with a partition of x, okay? And the partition of y depended on the partition we're using for x, right? So for each x increment, we partition the y increment, and the partition of the y increment depends on the value of x. Then when we integrate with respect to y, the limits will be in terms of x, so that when we get to this last expression, we have an integral that has just x's with respect to x. We don't have any y's in this integral. That would be inconvenient if we've already integrated with respect to y. But it won't happen if we've integrated with respect to y. Okay? Now, to get the average value, we also have to divide by the area of this thing. And you could just integrate 1 dy dx here, and you get the area. Okay? Or you can use the fact that it's a trapezoid. There's a formula for the variable trapezoid, just average the altitude multiplied by the width of the base. Okay. Now, that should give you a little deeper insight into what you're doing in section 2. And that would be a typical type of problem from section 2. Section 3, polar rectangle is Okay, if these were X's and Y's, you would see that this is just a rectangle from X equals A to X equals B, Y equals C to Y equals D, right? You just plain old rectangle. In polar coordinates, this doesn't give you what we see in 2 dimensions as a rectangle in the Cartesian plane. It gives you a section of a triangle. Let's see how that works. Now, really, you don't have a y-axis in polar coordinates, but we often draw one anyway, because we're drawing it within a Cartesian plane. Okay. Theta goes from A to B. Okay, right there is the line theta equals A. You know, maybe A is pi over 6. Okay. Probably a little more than that. Maybe it's about 33 degrees or something. And theta equals B might be here. Now, theta equals B might be over here. You might have a big pi shape or a little pi shape, okay? But when you confine theta between A and B, you're confining your region between 2 radial lines. And that should be obvious if you've been familiarized with polar coordinates, as you should have been pretty well in the prerequisite courses. Also, we did a little with them back in chapter 1. Okay, so there should be no mystery here. Now, R from C to D. Well, if R equals C, that means you're on the circle. R equals C. R equals D means you're on the circle. R equals D. So where's our region? Well, it's this region right in here, isn't it? Make sense? If it doesn't, ponder it till it does, because it's pretty straightforward. If we partition R, that means going to be intersecting this region with the arcs of circles with radii from C to D. Okay. So what we're saying is C equals R naught, which is less than R1, which is less than, et cetera, which is less than Rn, which is equal to D. And there's a typical partition there. Okay. So if R equals R4, well, here's R0, R1, R2, R3, here's R4. And the fourth increment goes from R3 to R4. Now remember, these are just arcs of concentric circles. R equals whatever, R equals R4 is the whole circle that this is only a little part of, okay? I didn't want to draw all the circles. It would have taxed my artistic abilities to the point of psychosis, okay? It would have messed up the picture even more. So that's what happens when we partition R. If we partition theta, well, you know, we're going to have A equals theta naught less than theta 1, less than, et cetera, all the way up to theta sub m equals B. Well, that means we're just going to have a bunch of straight lines here. So we partition R like this, and here's our partition of theta. Our typical increment can't read it. Here's our IJ increment. I messed up the writing of the word increment, but you should understand what I mean. Make sense? Now I'm going to exaggerate the shape of the IJ increment. You notice that the IJ increment okay, first of all, here's the line theta equals theta j minus 1. And here's the line theta equals theta j. Here's the arc, r equals r sub I minus 1. And here's the arc, r equals r sub I. You notice that you have straight lines with the theta equal cons, okay? Straight radial lines here and here. You have arcs here and here, arcs of circles, right? But you think in terms of very tiny increments, and if you look close enough at the arc of a circle, it looks straight. Notice that the earth looks flat, like if you're looking at the oceans. If you're looking around here, it looks all bumpy. Okay? The same way, these lines approach straight lines as you shrink these increments down, form your interval, right? Okay. So what's the area of this increment? Well, first of all, how long is this arc? This arc is a little shorter than this arc, isn't it? Okay, now your book does something a little different than what I'm doing. Your book says, I think, let's take the sample point halfway between here and here, something like that. Sample point's random. I prefer a random sample point. If you like the way the book does it, it works. I'm not saying anything wrong with it. I'm going to say we take a sample point here. R sub I star theta sub j star. And we're going to figure the dimension from that sample point. And we're going to approximate this width at the sample point is simply Ri star delta theta. Now that's actually the arc distance. If you multiply the radius by the angle subtended, you get the arc distance. That's the definition of a radian. And remember, we work in radians when we do real mathematics. Okay? We do not work in degrees unless we happen to work in degrees. But you got to have a real good reason to work in degrees if you're doing mathematics, because otherwise you've got to carry complicated conversion factors around with you and confuse yourself half to death. We're talking radian measure. If you don't understand why that's the arc distance, review radian measure and make sure you do. Okay? So that is it. So the dimensions of this thing, the width we're going to take to just be r sub I star delta theta. So let's say here it is again. Ignoring the fact that there's a little bit of an arc there and the arc distance is a little more than the distance from here to here. When we shrink it down, it's not going to make a difference. So your width is Ri star delta theta. And the length, let's say, is just delta R sub I. So the area is R sub I star delta theta delta R sub I. And you notice that even if your delta thetas and delta R's are constant, multiplying by Ri star makes these increments bigger as you move out away from the origin, right? I mean, you can see that, this is a bigger area than this one. Okay, now let's say we have function f of r theta. On the region that we talk about right here. If you just write out all the details, which you might not have time to do, so I'm just going to cut to the chase. Okay, the limits in the integral are going to be from a to b with respect to theta. And from c to d with respect to r. But delta r delta theta is not your area increment. R delta theta delta r, or r delta r delta theta is your area increment. So this is the area of a typical increment. And you multiply that by f of r theta, and you have the integral of this function over this increment. Written kind of small. I apologize. I always get caught in corners. Well, let me write it just a little bigger. Because of this, the integral of this function on the polar rectangle be written like this. Let's make that clear. Delta theta sub j delta r sub I. Okay, right here's your area increment, just as I set it down here, which approaches the integral I equals 1 to n. That's from C to D. That's your partition of R. And theta from 0 to m, and it should probably be m sub I, corresponding to the ith interval. The integral from A to B, f of r theta times r dr d theta. If you don't have a polar rectangle, like you have an ellipse, so if your region is part of an ellipse, then given your theta increments, you have different limits in your R, just like we had different limits on the trapezoid that we just saw. It's identical formally, but conceptually, getting your head around it, making it intuitive, you got to work some problems, which is why they're assigned. Okay? Make sense? All right. Now, there are a lot of things I could have covered instead of emphasizing this partition thing, but partition thing is going to make it a lot easier for you to understand what's coming. Okay? Try to get this stuff down as well as you can. I don't think it's a particularly difficult assignment. The integrals are not that difficult. You know, I look over these integrals and they're all pretty straightforward. Once in a while, a little curveball, but I don't think I assigned a lot of curveballs. Okay? And they talk about type 1 regions and type 2 regions and so forth. I haven't talked much about that, but it should be kind of obvious from the exam what you do. Sometimes you want to cut the regions this way, sometimes you want to cut them that way. That trapezoid that I drew real quickly, if we got a region like this, different slope here than here, we don't want to cut it this way. Because if we cut it by y values, we got 3 different regions. On this region, if we cut it with y values for a given y value, x goes from this left boundary to this lower line. In this region, it goes from the left line to the right line. In this region, it goes from the upper boundary to the right line. It's three separate regions. Whereas if you partition it with x, you've just got one region. That's what it comes down to. And sometimes it's the opposite. Sometimes it's easier to partition the y's and then the x's in terms of that. Okay. If you understand the concept, I don't think you'll have too much trouble applying it, but when I get your homework and take a look at it, I might find that we need to talk about a couple more things. And if you have questions, email me. Okay. Of course, if you got questions, you can come by during office hours too. I'll be around all afternoon. Most of you have lives and stuff.